Okay, we're live, and then I'll begin by sharing the screen. Now, I was a little bit sick over the week, but hopefully I'll be able to give this talk without any issues. So we're going to share that. No, wrong. In order to do this properly, I remember we had this problem last time. I need to share full screen, don't I? Entire screen. There we go. Share. I'll select. Hide that. So we go, no, that's wrong. Quit. Right. This is the one we want. Okay, so it's a general title for this talk on the anamorphic universe model, sort of just general research. I can kind of move through the slides this way or this way. Okay, that's probably the better way to do it. So to begin, we'll just do a brief recap on the Ohm hypothesis. So the anamorphic universe model, as I've talked about before, sort of leverages stereographic projection. So I just have a bit of a slide here with kind of a visual demonstration of what stereographic projection actually is and what it does. Down at the bottom here, I've mentioned forwards and backwards transformations, although that terminology doesn't really apply in a sense. You'd have like inverse and I guess standard or something like that. But basically what I mean by that is the forwards. So let's say we have data on the tangent space or tangent plane, and then to forward transform it stereographically means to place it on the sphere. So going up one dimension from 2D to 3D or 3D to 4D. And then the backwards transformation simply takes the data that we put on the sphere and projects it back onto the tangent space, especially after rotation or some sort of scaling factor. So we'll look at that next. So for the 4D stereographic projection here, I'm speaking about the backwards transformation. So from the hypersphere onto the tangent space. And to do this, we're taking data from the Sloan Digital Sky Survey. So all the positions of the galaxies with the right ascension, declination, and Z redshift. And then, so after we've projected it onto the hypersphere, then we can rotate and scale the hypersphere using these transformations here, and then project it back into the tangent space. So we have theta, which is some value between 0 and 2 pi, but we just want pi rotations because when you want to turn the universe inside out stereographically, that's what we require. So here's an example of that. The blue dots here are the positions of the galaxies relative to Earth, which would be at the very center of the red dot, but ignore the red dot for a second. So when we forward transform the galaxy positions onto the hypersphere, or even just onto a sphere in this case, and then rotate and scale the universe down by 70 times, so 1/70, and then reproject it onto the tangent space, we get all the galaxies in the universe are compressed into the red square here. So we can imagine that the universe, all of the matter began in this phase here, and then erupted in what we would refer to as the Big Bang, and inverted to become possibly antimatter, which explains where the missing antimatter goes, especially if we think of mass as decreasing the further we go out, just as Dr. Gims says. So yeah, and then at the end of the universe, we can imagine that all of the stars and galaxies will rotate back into the center, thus obliterating the Earth. Notice I say not all life on Earth will be obliterated, but that's something I mention in papers I've written, but I'm not going to go into why that is in this talk because it's a little bit too in depth and it's not part of the talk. So you notice there's no actual singularity in this creation destruction event of the universe. It's just a rotation of the hypersphere. So that's why I've represented this image as a kind of topology which shows no singularity. This kind of topology, though, is used for de Sitter space, which is similar to what I'm talking about in terms of that it has a projection onto a surface. Although that surface it has a holographic projection, which is very interesting and could be the case on the hypersphere, although it doesn't necessarily need to be the case. So yeah, I mean, there's problems with de Sitter space, though. It's been dropped for several reasons, but essentially it's looking to unify or extrapolate from Einstein's general relativity theory and apply it to the whole universe. But as we mentioned, it doesn't have it's wrong in some respects, and it's missing key features which I think the anamorphic universe model has, and why this model is so much better. So the structure of the presentation is as follows. To begin with, I'd like to just post some corrections about mistakes I made in a previous presentation on this subject, specifically on the area of time dilation from the hypersphere to the tangent space, and those of the dimensions of the universe, which I also got wrong. I think we've corrected that through the support vector machines, but I'll just briefly go over how that's achieved. Then we'll look at the expansion rate of the universe, the Legendre transforms. We'll also apply the ideal gas law then to those transforms. We'll look at a TOE, theory of everything, which is a unification of gravity and electromagnetism, which is distinct from grand unified field theories, or GUTS. Then we'll look at elliptic curve cryptography and modular forms and their applications to this subject. And then we'll get into the actual how do we say, the kind of the meat of the talk, which is, did the universe have a false start? Or, well, that's the title of this presentation. As myself and Rajan know, that the presentation had a bit of a false start earlier with sound issues, but they're fixed now, so hopefully. And we have the Riemann Zeta function. We're going to look into that to see how we can apply the elliptic curve to the Riemann Zeta function, if possible, and then a brief description of future work. So let's begin with the rata from the earlier presentation. In that presentation, I spoke of time dilation, and I think I was saying that, well, I'll just issue the correction, and then I can say what was previously wrong. So we understand that light moves in straight lines on the tangent space, but curved lines on the hypersphere. And that's represented by the red and the yellow lines here. So the speed of light is a constant on the hypersphere, and this ensures that light slows down as a function of distance on the tangent plane. So originally I had stated that the speed of light was constant on the hypersphere. I'd done that to kind of, I just reformulated it to fix some issue, but I was supposed to turn it back, but then I kind of forgot about it. Yeah, so we can still use the because we have time dilation on the tangent plane now. We can use that as time dilation for supernovae type 1a as they go further out. We notice that they evolve slower the further they go out. But even that wouldn't account for all of the time dilation that we expect to see with the supernovae. So possibly the rotation of the hypersphere gives an extra amount, or there could be an additional amount due to the compression of the lines. There could be a logarithmic compression, or an additional linear feature added to the logarithmic compression. But that is something that we'll have to look into later on to find out if that's correct or not. Continuing on from, well, this was less, well, I suppose this is to do with time dilation as well, but this is also more to do with where the boundary of the hypersphere is located in the tangent space. Previously, I used this graph, which I had misread, and I thought this was looking at multiple examples of supernovae spread out across space, and that this was the time dilation, and that there was minus 50 days and plus 300 days. So I was looking for the point at which the redshift was 0, which would equal the hypersphere surface. But more importantly, I was interested in the distance to the Earth, you know, so the blue shift distance essentially. But it actually turns out that these are the relative flux of a single supernovae called SN 1994H, and so this is not useful in any sense. So that this is just a range of possible time dilation effects that we might see. So that's why I'm going to further issue a correction on how to actually find out the redshift distance, because we were using this to create the dimensions of the hypersphere, and obviously we can't do that, which is why the original dimensions were incorrect. So hopefully this correction is better. So how did we go about finding the dimensions of the hypersphere? Well, we used support vector machines, and we'll just go into that quickly here. The Gaussian radial basis function kernel trick. So here's just a quick summary of support vector machines and how they work. They are, particularly the kernel trick is used for the classification of nonlinear data, which in our case is useful because we have the untransformed galaxies and the transformed galaxies. So we want to know where is the decision boundary between those two classifications. And it's nonlinear, obviously, so that's why we need this kernel trick. So we use the radial basis function kernel and a cost function of C1. And the results are as follows. So obviously the dark purple galaxies are the untransformed data points from the DSS catalog, and the yellow ones are the transformed ones. So they've been scaled and rotated. And we can see that the red line here, the cost function of 1 is the decision boundary between the two classifications. But interestingly enough, we have so the cost function of 1 is a fairly common cost function to use. If we use a different cost function, we can make this line closer in or further out. But so I think it's interesting that the line should be outside the first great wall of galaxies. So we would expect that since this is on these transformed galaxies are obviously inside the first hypersphere of the inner sphere of the hypersphere, and this is the interstitial realm out here, and then outside here is the outer sphere of the hypersphere. Then, you know, we know that these galaxies in the interstitial area don't transform. Well, they would transform in a way, but they will never move either to the outside or the inside, well, depending on the rotation that you apply, obviously. And similarly with the galaxies on the surface of the hypersphere, they will only transform on the surface, so they don't move in or out either. So that is interesting that they are also kind of on the wrong side of the hypersphere decision boundary of the hyperplane. So we can measure the distance from the Earth to these to the Great Wall, and we get a distance of 43.2 megaparsecs, and they have Z redshift of 0.01, which is quite low, obviously. Now, I should say that we were using Hubble constant of 70 and a flat space-time to do that. Also, the angular distance, I think it is called. But we'll get to that later on. But before we do, it's important to kind of look into 4D geometry and how, because so we have the outer cube here, which is this entire hypercube or tesseract is inscribed within the hypersphere that I'm talking about. So the points of the outer cube touch the points of the outer sphere of the hypersphere, and same with the inner cube here. But from a four-dimensional perspective, so if we were to measure the distance of the outer cube, this is the 3D projection. So if we measure the distance of the outer cube to the central point and the inner cube to the central point, we're going to get two different answers. So obviously out here it's 43.2 megaparsecs, and the inside is 21.6 megaparsecs. But from a four-dimensional perspective, both of these distances are going to be the same. And we can work it out using this equation here, which is, generates this cube. And then, so then when we do that and we take the four-dimensional Euclidean distance of all the points to the central points from a four-dimensional perspective, the answer is 14.4 megaparsecs. So that's going to be our radius. So from that, we can calculate the dimensions of the hypersphere. So here we have them. We have a radius of 14.4 megaparsecs. Diameter is just twice that, so 28.8. The circumference can be, defined from the radius, simply using 2 pi r, and that gives 0.4778 megaparsecs squared. It's squared because it's a four-dimensional circumference. Surface area is the first derivative of the volume with respect to r, and that gives 58.9 gigaparsecs cubed. So once again, the surface area of the hypersphere is equivalent to the tangent space, so it is a three-dimensional area, or volume, actually, all of space. Then the 4D volume of the hypersphere is, so it's the full volume of the hypersphere is 212 gigaparsecs to the fourth. And this just shows the base parameters I used to measure the original 43.2 megaparsecs, which was angular size distance, a Hubble constant of 70, and a flat universe. Okay, so now that we have the size of the universe, and we can look at the expansion rate of the universe. So yeah, well, we know that the universe scaled by a factor of 17 upon the initial rotation, because that number allows us to compress all of the galaxies inside of the inner sphere of the hypersphere. So we have this number 70, which is the answer to something called the Lucas Cannonball Problem, which is stated a square pyramid of cannonballs contains a square number of cannonballs only when it has 24 cannonballs along its base. And so we can see that square 70, the sum of 1 to 24, each of those are squared. So we have this relationship between the number 24 and the number 70. So the solution to this problem is also important in other areas of physics, such as heterotic string theory, In particular, we have the Leech Lattice, which can be constructed from the Lorentzian Lattice to the 26-dimensional one. So the fundamental roots of this lattice are the points or, such that or times or equals 2 and or times w equals -1, where w, or probably omega, is the Weyl vector. Oh no, maybe w probably stands for Weyl vector actually. And so you can see there, so it's 25 dimensions of 0 to up to 24, and then the space-like dimensions, or the space vectors coordinates, and then the time coordinate is oh, that's wrong actually, that shouldn't be less than 70, that should be -70. Don't know how that got in there. So, and it's obviously minus because that's the time coordinate here. So in string theory, heterotic string theory, they were looking at these as the space coordinates, this is the time coordinate. We're not applying it in that sense, although, yeah, so in the 26-dimensional Lorentz lattice, the Weyl vector is a light-like vector. Although I actually did find that result a bit difficult to prove, because I think if you have two vectors and you take the norm 2 of them, really what you're looking for is the dot product, although those are basically very similar. So, but if you get a result which is 1, then that's a space-like vector. But if you get a minus 1, then that's a time-like vector. And then if the dot product is 0, it implies a light-like vector. So it's traveling at the speed of light along that kind of 45-degree angle in a hyperbolic space. So, but you would imagine that any two vectors that are identical will produce a 0 in when you take their dot product. So I would question why that's so interesting in terms of the Weyl vector. But then again, when you actually do take the dot product of this vector, you get 9,800, which is a multiple of 70, which is interesting. But it's, so maybe if you're talking about taking the mod of it, then that gives you a 0, but I don't think that's what they're suggesting. So there must be some step that I'm missing in order to do that. But we're not really interested in Weyl vectors and light vectors in that sense, although they could be applied in some way. But we're just talking about the link between the number 70 and the number 24, which, so if we have the number, a link between the scaling factor and then the number 24, then we can say, well, the amount of time it took the universe to expand to, 70 times its size was 24. So, but, the most obvious kind of division of time in terms of 24 is 24 hours. I mean, it's the first one to kind of think of. So therefore, the universe expanded to its current size within 24 hours. So we can use this function here, which is sort of the linear sum of the square root of n, where n is any of these in this list. And then the result is the first one, well, if we start at 0, a bit like, because the Weyl vector included 0, so we might as well include it ourselves. Then it goes from 0 or 1 all the way up to 70. So that is the scaling factor of the universe. The average of this scaling factor is approximately 28.8, which is a harmonic of the diameter of the hypersphere at 28.8 megaparsecs. That's kind of an interesting feature of the scaling factor. So if we apply the scaling factor to the current size of the universe, using the 4D circumference, we can then extrapolate backwards to see the different various sizes that the universe had during that 24-hour period, and we see that it started off the circumference began at 1.29 megaparsecs squared and expanded up to 90 megaparsecs squared. We can do the same with the surface area expansion of the universe. We see that it began at 0.8 gigaparsecs cubed and winds up around 58.9 gigaparsecs cubed. So that's the surface area. And then the volumetric expansion would be 3.03 gigaparsecs cubed to 212, roughly, gigaparsecs. So we can see that the trends are the same in each graph, and that's to be expected because it's all just based on the scaling factor. We can also calculate the growth rate by different means, which gives us a different type of curve, which shows that within the first 24 hours, there was greater expansion at the beginning and kind of tapers off towards the end. So that's that. But so one of the issues about all of the previous graphs that I showed you was that they were all discrete quantities based on the scaling factor, which is a Diophantine equation. So it only deals with integer solutions or integer solutions to integer coefficients. So we want to make, well, it would be nice to find a continuous function to do that. Luckily, that already exists because we have the, we have the Diophantine equation here, which can be expressed as an integer solution. But this is also an elliptic curve, which when we plot it as an elliptic curve, or this is the elliptic curve solution to the Diophantine equation, I should say, we get this, which is a smooth and continuous curve. So if we wanted to take the Legendre transform, let's say, of the volumetric expansion to get the pressure differentials over the 24-hour period, we'd be better off using a continuous curve, or so we'd imagine. But yeah, as we'll see later, there are problems with that. But there are other useful areas of application for this elliptic curve. Plotting the first 4 hours of expansion. So this is the hypersphere sort of radius after 1 hour. Yeah, and then after 2 hours, 3 hours, and 4 hours. So you can see how the elliptic curve kind of, if you follow it along, you get to this point, and this is, you can go take the value of the y-axis. It'll be 1 here, 2.23 here, and so forth. So that's the relationship between these two things. It also, if you try and, obviously this is just a 2D diagram, but if you were to imagine this as a 3D projection, then you can see that these lines kind of give you a sense of the slope of a cone in a sense. And then the egg shape here, it's like a droplet of water that comes up off the top. The other thing we can do with the elliptic curve of the scaling factor is we can extrapolate. So what would the size of the hypersphere be after after 2 days of expansion, or 3, or even a week? And so these are the values that we get here. So after a full week of expansion, the scaling factor becomes 1,262, which is 1,260 is a fairly auspicious number. So, but we see that had it continued to expand at the rate of the scaling factor, it would have a volume of I think this is actually megaparsecs. Oh no, sorry, yeah, it would be 591,000 gigaparsecs to the 4th order after 1 additional day, 1 million gigaparsecs to the power of 4 after 2 days, and roughly 4 million gigaparsecs to the 4th after 7 days. So, so that's just an interesting extrapolation that we can do. So now we'll move on to Legendre transforms and look at volume, pressure, temperature, and entropy of the system. So here's just a quick sort of definition of Legendre transforms. In physics context where f is a function of x, the Legendre transform can be defined as follows. So we have a differential function where we're taking the Legendre transforms of this. So yeah, we say that df over dx is p. So then we can rewrite this as just p times d, the differential of x. And then using the Leibniz rule, you can transform this into x times p minus f. So this function can only be used if the derivative of the original function is positive, and or if the function is monotonic. So let's see if that's the case. And we see that the original elliptic curve is non-monotonic anywhere on the real line. It has a stationary maximum critical point here, and stationary minimum is here. So unfortunately, we cannot take the Legendre transform of this curve. So, but there might be other ways to do it. One option is to just go point by point, which is what I did here. So this is the discrete Legendre transform of the surface area expansion of the universe using meters and pascals. So here we have the expansion of the surface area in blue and the pressure differential over that time period drops as follows. And these are the different values here. So all of these minus signs are actually on the wrong side. I think they should be over here. So these are all technically minus signs, but they can be flipped to get the how it's dropping. But that might need to be minused from an initial pressure value, which is something we'll have to look into. Right. So then we can take the discrete. Right. So first we did the surface area. Now we can do it with the volumetric expansion. We get similar values here. So minus 8.8 to power of 10 to the 99th is the end result there. So now, since we have the volume and we have the pressure, we can attempt to apply the ideal gas law in some idea of that. So the ideal gas law is the pressure times the volume equals the amount of substance n, the ideal gas constant, and the initial or the temperature. So the temperature of the universe is usually defined by the cosmic microwave background radiation, and it's around 2.72 Kelvin. So if we take the ideal gas law and in terms of n, then it's pressure times volume divided by the ideal gas constant times the temperature, which we know. So, and we also know the ideal gas law. So this implies that the amount of substance in the universe is 5.3938 10 to the power of 162 kind of particles, but that could include galaxies as particles. So so yeah, this says moles, or galaxies, I'm saying, because when applying ideal gas law to the entire universe, we're looking at galaxies instead of moles, really. So since we already know the temperature of the universe, we can extrapolate backwards to get the temperature differential using so dt over the differential of the time, and yeah, using the ideal gas law. Right. So that's how we get that, and then we can take the discrete Legendre transform of the temperature differential to get the entropy. So this looks like the entropy in Boltzmann's doesn't change as much as you'd expect, although it changes just as much as you'd expect in a universe that didn't have a singularity. So it starts off with quite a minor change, then increases kind of dramatically. So, but not too much, and the end result is around 25.12 Boltzmanns of entropy. So obviously these values can be used in a greater context later on, but those are the values I've discovered so far. One way that we can use this research is in the unification of gravity and the electromagnetic field. So we'll look at that, potentially at least. If we look at the electric force, the strength of the Coulomb force versus the strength of the gravitational force, that is around the difference that we expect to see is that the electric force between a proton and electron, I believe. Oh no, sorry, the difference between an electron and an electron is 1.2 times 10 to the 36, stronger than gravity. And the electric force between a proton and an electron is 2.4 times 10 to the 43, stronger than gravity. So we're looking for these kind of ratios in the anamorphic universe model. And what we find is that using the surface area pressure, which is Pascal's to the third, so we want to take the square root of that, obviously, or the third order square root, and then divide that by g, gives us, right, so there's the pressure, in Pascals, divided by g gives 4.09 10 to the 37. So that's kind of, it's in this range here. But I think probably a better one to use is the volume pressure. So that is the fourth squared root divided by g gives 1.45 10 to the 35th power. So I think that's kind of better. It's also better because if we take the third order square root, I'm not sure if we're going to say that, of g, we get 3.09 e to the 43. So it's similar to this one. So it seems like taking the volume pressure in pascals is more useful than the surface area, which is for unifying electricity and gravity. And the reason why we say it's a unification is because we're using the whole system to achieve these results. So it's kind of unexpected that we would get those answers. There's also other things we could use for the unification of gravity and EM. So if we look at the value of the gravitational constant in terms of parsecs, it is this value here. And then we take the circumference in parsecs, then we can multiply the force, or the force by the area, essentially 2 times c on the bubble universe, to get 1.15 times 10 to the 31 meters to the 5th per kilogram second squared. And that works out, so that this then if we divide by g, which we can take the we don't have to use the parsec version here because we can see this has been converted into slightly into different units. So if we then divide, we can see that this is 1.72 e to the 41, which is kind of close to the electric force between the proton and the electron. So there's more to be said about that, but this is just a different way of doing the calculation, if you like. And then this image here is the the quadrupole of the CMB that I just kind of made up in Photoshop using Gaussian filters. So I just thought I'd throw that in there. I think it's kind of a nice image. It's fun to try and recreate the dipoles from the CMB. Earlier we saw the the quadrupole. Earlier we saw the dipole. So these units here are also related to I think the Fermi constant, but they're kind of inverted. So there might be some link here going to the Fermi constant as well. This entire equation, though, is what it's really talking about, because if we have a bubble universe and we have the surface tension times the area equals the force of on the bubble, essentially. So this number here, therefore, represents the universal force for gravity, which is obviously a good bit bigger because it's 10 to the 31. So it's also interesting that it's meters to the 5th, so it's something to look into. Let's see if we can continue on here. Oh yeah, so we'll apply the scaling factor to elliptic curve cryptography and modular forms in this section. So if we wanted to apply the Diophantine equation to elliptic curve cryptography, we need to plot the scaling factor of the elliptic curve over a finite field P, where P is a prime number. And obviously, choosing P in this instance isn't very difficult because, as we know, there are 24 Leech Lattice. There are 24 even unimodular lattices, one of which is the Leech Lattice, and there are 23 holes in the Leech Lattice, and well, 23 therefore could be equal to the number of holes in the lattice, or one less the total number of Leech lattices, of even unimodular lattices, I mean. So the yellow points here, we simply evaluate the curve mod P, and we get these. So then in elliptic curves, we have two various starting coordinates, A and B, and then we can start plotting the windings, which is how this kind of links back to string theory in a way. So here's some of the windings that we get around the finite fields of 23. These are just some sort of random examples. So if A starts at 5, 3 coordinates and B is 22, 0, A plus B will be this point here, which is probably looks to be about 13, 2. And we can see the windings here and the windings here. So there are possible ways to apply this to physics, but it hasn't been fully achieved yet. That's still sort of in the works. But I just think this is interesting, and the connection back to some of the mathematics of string theory is also pretty cool. So you can see how they would have been kind of obsessed with this, these kind of windings around toruses, tori. Yeah, so to take the modular form and graph them of the original elliptic curve that we have, we need to find its Weierstrass normal form. We do that with the Jacobian, and we wind up with this equation here, which we can plot, and we can see that it has similarities, but it is quite different as well. So when we take the modular form of the normal elliptic curve, these are some of the results. So you can see it's quite interesting. It looks like, well, I'll just continue on. We'll see the different components that are in that are in that modular form. So the modular form of the elliptic curve E, the expansion Q is, or the Q expansion is defined thusly. Now, looks like there's some errors here. It's not translating properly, but this is the sum of n equals 1 to infinity a sub n q to the n, where q is equal to essentially the Euler equation. So this question mark here is pi. So it's a rotational equation. Then the conductor of the elliptic curve is also Ramanujan's taxicab number 1728, which is 12 cubed. The discriminant is some large negative number. And then the Sato-Tate group is the SU2 special unitary matrices of order 2, which is interesting because that ties in a lot with obviously determining the spins of fermions, as well as relates to Bloch sphere and therefore to polarization. And we have it in the the Pauli matrices. Then we can think of them as a special case of, what would they be? They're a subgroup of SL2Z. And actually, if we go back here, so this modular form looks a lot like SL2Z anyway along the edges. So looks like there's some relationship then between the elliptic curve that we're talking about and fermions, as well as just the expansion of the universe and all of its relationships to volume, pressure, and then the link between gravity and electromagnetism. So this does feel like it's becoming very unified. And the first 50 coefficients of this Q expansion are as follows. And then if we take enough of them, we can start plotting these modular forms. And then the infinite hyperbolic tiling of this modular form kind of comes out looking like this. And it's interesting on how we should interpret this. I like to think of this as maybe the present moment here, and then it stretches off into an infinite past, an infinite future. So this is in some sense outside of the universe, because we know that the universe didn't have an infinite past. It began at some point. And it'd be interesting to see if this curved line here is the same as our Diophantine equation curve. But we'll have to look into that. It's just something that's occurred to me now. And then obviously it gives the idea of some kind of multiverse as well, because we can see that it's branching off into infinite different areas. So yeah, I just like that kind of concept. And since a lot of these a lot of this mathematics to do with the elliptic curves and the Weyl vectors and such, that was all work that was done by Orchards. Since a lot of that has been applied to string theory, and then these graphs appear to give us a sense of some sort of multiverse, we can ask, well, should we really start applying the mathematics of string theory to the multiverse instead of just string theory? Because obviously there's question marks hanging over the validity of some of the methods used in string theory to actually achieve its end goals. Anyway, so let's get to the main topic today. Did the universe have a false start? A lot of this is informed again by the elliptic curve, because if we take this literally, well, we have the start of the universe here and then it begins to expand. Well and good, but what about this egg-shaped thing here? If this is time moving in this direction, then it looks like the universe began here at point -1, 0 and expanded, and then stopped again at -0.5, 0, and then before beginning again at 0, 0. So we can look at it. We've already looked at the non-monotonic curve that this elliptic curve is kind of based on, and so we know that we have the maximum critical point and minimum critical point, if you like, is but the maximum critical point of the egg is are these two numbers here. So this gives us a maximum scaling factor of around 0.126. And so the volume of the proto-hyperspace bubble would have been 383.8752 megaparsecs to the fourth power. So here it says on the x-axis, the proto-bubble appears to last for -1/2 hours, which obviously doesn't mean anything. It's kind of funny. However, this is misleading as no duration is applied to changes in the scaling factor, especially when the universe has already reached its full size. You know, that happened after 24 hours, but it remains at its full size, you know, over the lifespan of the universe. So this cannot be seen as a, you know, the x-axis here cannot be seen as the total time series. So the point I'm making is that this bubble universe could have lasted for an infinite amount of time or anything up to that before coming to an end, and then this expansion rate beginning. So that's kind of misleading there. So the maximum critical point and its possible relationship to the Higgs potential needs to be addressed, because if we look at the y-coordinate, we have 0.126, which is very close to the value of the Higgs mass, which is generally cited as about 125.5 GeV. These numbers also appear in and are applied in many areas, other areas of mathematics, such as Gauss-Legendre quadratures, which is kind of what this curve is really. It looks like a quadrature. And the flow of liquids, which is also interesting as it comes back to surface tensions and bubbles and things that we're looking into anyway in terms of gravity and electromagnetism. Simplex noise generation and the rotation of the points of tetrahedrons, just to name a few. So the y value of the maximum critical point is proportional to the Higgs mass, as we mentioned before. And if this is then the potential, then we'd imagine that the vacuum expectation lies within the sort of the trough of this curve. But we find that that point would be the minimum critical point, would only equal 211.3248 GeV. And the actual vacuum expectation value is a little higher than that at 246.22 GeV. Can use this to figure out the mass of the W boson using the weak isospin coupling in natural units. So if we were to replace the current value of the vacuum expectation value with our new expectation value, we'll see that the answer comes out for the mass of the W boson, that is, comes out at 68 GeV, roughly, or 68.99 GeV, which is obviously incorrect. So there needs to be some work done here, possibly in terms of gauge group stuff, but we'll look into that later because it's not fully finalized yet. But instead, I want to look at how the elliptic curve might connect to the Riemann Zeta function. So here we see a definition of the Riemann Zeta, or Euler-Riemann Zeta function, which is the sum of these complex fractions, if you like. And for, yeah, so the Riemann Zeta has an analytic continuation for everything below 1. So here we see it plotted along with the elliptic curve for the scaling factor of the universe. You see that there's definitely some sort of connection between the two, or I like to think so anyway. Or that's the impression I'm getting, and I will sort of defend that or provide my justifications for it here in this talk. So if correct, then we see that the proto-universe begins at the point -1, 0, I actually, which is there, which is obviously less than 1. So this is analytically continued and can be, and the point -1 can be expressed as the sum of all the natural numbers, which gives the value -1/12 in according to the analytic continuation. So that suggests that there's a relationship between this infinite sum and -1/12 and the beginning of the proto-universe, which is why that we can, make the assertion that, well, maybe the proto-universe has this, it began at infinity, it is infinite, and so it always exists, and that's perfectly in line with what we're talking about here. So we'll move on. We can see that the universe is currently centered on the cusp at 1, 0, exactly 1. Oh yeah, I said currently. I should say exactly 1 after it was created. So here's the hyperspheric expansion after 1 hour, and here it is. You can imagine if you put the circle over here, it is centered on the cusp here. Oh, and we notice that the elliptic curve then skirts and crosses here, which is kind of equivalent to this. So this is an interesting characteristic of the thing. So then if we scale the hyperspheric universe bubble by 70 and overlay it over the Riemann Zeta function, we see some interesting sort of aspects that can be addressed later on. For instance, the projective point on the hypersphere would lie at 0, 140i, and it has a z value of 1. So that's kind of interesting. Therefore, if we were to extrapolate this into a 4-dimensional model, it would be 0, 140i, 0, 0, 1, which is those 4 coordinates. And so the Riemann Zeta function ostensibly provides quantitative data on what is inside, below, and outside the hypersphere from a 4D perspective, which is interesting because this is something that we would otherwise just not have any information on. So we can kind of look at that. It looks like that everything above the tangent plane is fairly uniform. It's the numbers increase considerably as you go up here and decrease as you get in here, obviously. And then there are these kind of staves, these purple lines like a fence, which come up from the critical line, which would be equivalent to the tangent space. Or the tangent plane onto which the universe is projected. And then we have our location, the location of the Milky Way galaxy, which is centered on the elliptic curve, which is one of these lines here going out, which kind of look like the light rays almost being refracted through a bubble. And then beneath that, we have this sort of seeming chaos, which is the analytic continuation of the Riemann Zeta function. So that's interesting as well. If we look at a bit of a close-up view of the center where just our location in the 4D bulk space, we see might as well comment on these purple staves that I was talking about. And we see that they're roughly spaced about 9 units on the x-axis. Then we ask if they could be responsible in some way for quantized redshift, which is periodic, also called periodic redshift, which proceeds in roughly multiples of 3. I think it's like 0.3. I have to. There's different ways of calculating that. So there might be some relationship there. and move on. So finally, we'll look at future work. One kind of interesting area of possible research is into 3D elliptic curves. So if we were to just plot any one example of an elliptic curve here, this is the kind of thing we get when we try and plot it as a 3D surface. This is a very good graphic showing how cross sections of that 3D surface we saw produces the kind of egg shapes and planar lines that we expect from 3D elliptic curves. And there was the source for that graphic is there below that, below the image in that slide with the animation. So, but there's another way that we could look at 3D elliptic curves. Is it because most of them, they only seem to really show half the story. And it appears to be a lower dimensional representation of a full 3D curve. So if it's half the story and there's this relationship between tori and elliptic curves, then maybe by joining these two opposite curves together, we see here, we could get the full picture. And so we can do that, and it kind of creates sort of a bridge, if you like. So this could be effectively a stereographically projected torus with one part orientated towards the projective point. This is just another quick example of how you might do, what's the word? Oh yeah, a 3D representation of an elliptic curve. You can see it kind of has this sort of doorknob shape or something. But possibly a better way to do it would be to follow this torus angle and, you know, generate something like this using these kind of equations up here, which have, they have 7 coefficients, whereas you know, the normal Weierstrass form only has 2 coefficients, and then the long form has 5. So if we're taking it up to 3 dimensions from 2, maybe it makes sense that they have 7. So it goes 2, 5, 7. Again, we have the Clifford torus, which is a stereographically projected and rotated torus. And then next to it, we have the 3D elliptic curve. We see that at a certain point in the rotation, this matches this. And it's actually at this exact point that it's frozen, more or less. If it moved on 1 or 2 more frames, that would be the correct version. Here's another example of a stereographically projected torus. In this case, it's actually a cycloid, which might be more accurate. So I'm thinking we need to find a 3D elliptic curve or stereographically projected cycloid that links back to the full start of the universe. So I'm dubbing Eden because it's sort of this infinite proto-universe, although that's not really quite accurate in any sense from a biblical perspective, let's say. Another area of research that would be interesting to do would be to continue on the research into elliptic curve cryptography and how it relates to the scaling factor of the universe. So plotting the torus of finding the modular points with these yellow points and plotting them on the torus and applying various aspects of string theory and the Weyl vector of the Lorentzian lattices to the multiverse. And also, more importantly, I think actually we'll be applying the Higgs potential to this and other, because if we take the you know, the points on the elliptic curve where we had the maximum critical point and the minimum critical point, and then we do a kind of a gauge transformation that could take us from the so if this is the proto-universe here, this is the scaling factor going off here, then the torus obviously links the proto-universe with the current universe, which would be scaled to 70 on this side. which kind of produces the how do you say it? The asymmetry between the proto-universe here and the scaled universe in the background there. And then we could use group law. So we could plot that on something like this, and then use on the finite field, then use group law and the gauge group to find the actual value for the vacuum expectation value at 246 GeV, and then find the Y value for that, and then start doing group law to find other constants. So that could be an interesting thing. Also, finding the length of this red line when we've achieved all of the previous steps would be could give interesting results. And I've found that preliminary research seems to suggest that if you don't take the square root of the resulting values, when you reach the VAB value, you wind up with the constant of where the electroweak symmetry breaking happens, which is around 159 GeV, I think. So that becomes the Y coordinate. And then when we plot all of that into the finite field and take the length of that line, it turns out to be very close to the mass of the top quark. It's just an interesting thing. Finally, I'll finish with some references. They're in no particular order, and some various links that might be useful. Okay, so that's the end of that. Thank you. How do we get out of this? It was a little longer.
Excellent presentation.
Oh, thanks very much.
Excellent presentation.
How long was that?
It was about little over 1 hour, I think.
Oh my God, sorry. I spoke very slowly because it's quite a lot of information.
But I think, yeah, we may have something, we talked, I don't know whether it's exactly when you put live, it started, it may be like, may have started only after a little while. So the live thing shows about 1 hour, 7 minutes.
Yeah.
But it could be
I think
less
that's
than
about
that.
right. I think it did take about an hour, yeah. I was thinking at certain times, I was thinking, oh, I should speed this up. But then there were so many little kind of details that my mind was like going to. It was like, oh, I should mention this. And, and I think it was probably good that I did that, because then I was kind of able to wrap things up. But I'm just not sure how interesting that is for the listener. But oh well,
yeah.
What can you do?
These topics a lot of many different things you have put together, but but interesting. I think it'll take a while for you to unwind everything and then look at each part, and then
That's
I think
it
points to different projects. That's what I see.
It does. There's a lot of projects there. That's kind of one thing that I'm hoping to do, by presenting this work, is to see if other people want to sort of join up and join forces. So there could be different avenues of research that could be followed up. Like for instance, the Lagrangian. If there was some wave function that we were able to get from, let's say, the modular form or something, then I could send it on to you. You could do some work, produce the Lagrangian for that, or I could, I'm sure someone watching or one of the members of the TEGS group could, just to speed things up a bit, even I don't know, maybe doing some work writing papers together and stuff. Yeah, so I'm going to continue on anyway, whether I'm joined by anyone or not, but it's just my thinking. I'd like, at certain points, hopefully the work will become interesting enough that someone will say, oh yeah, I think this is correct, and I want to also work on this topic. I mean, it looks like, if everything is correct there's a lot of linkages to string theory, possibly expanding into the multiverse, although that is very early days on that particular subject. And then, of course, I mean, what are some other aspects? We've got the modular forms, linking back to potentially sort of SU2 groups. And then, of course, the big one in terms of unifying gravity and electromagnetism on using the volume of the hypersphere. So that's pretty cool. And then, of course, when we start looking more concretely later on into how surface tension models on the bubble universe, you know, so basically we have surface tension equals the current gravitational constant, and then but if we take that and multiply it by the area, which is actually the circumference on the bubble, then we get the total force on the bubble surface. And so that is like a new value for gravity that's not really been defined before. So that's going to be interesting as well. And then there's an awful lot of work to be done then with the surface tension gravity, and you know, beyond that, like, what is it, a bubble or is it a droplet of water? You know, so does it have two sides to this surface tension or just one? So that's going to be interesting. And it does look like that the research that I presented today, you know, kind of does give us some idea of what's inside the bubble, in a sense. So even if it is a bubble, there's still information, you know, air, if you like, contained within it. And that air can be described via the X, Y, and Z components of the Riemann Zeta function. And so I think that's possibly useful. Also, we can talk about mapping the Riemann Zeta function onto the surface plane, onto the surface tangent. We can also talk about what's outside the hypersphere. We can talk about what's below the tangent plane, and that's only the upper. I think, am I correct in saying that usually when you I might have to look into this actually, but I know that when you're dealing with the Riemann hypersphere, you're usually talking about the upper half plane. And certainly with modular forms, you're also only speaking about the upper half plane. So I think that's also the case with the Riemann Zeta function. Like I say, I have to look into that. But even if we were to take the Riemann Zeta function and map it onto a Riemann sphere, then we definitely would only be on the upper half plane. And so that is interesting. I think that's probably a good idea anyway. I know it's been done before, but I mean, it just makes sense because we're dealing with hyperspheres anyway and projections. So inevitably, it's going to be projected onto the hypersphere, making it a Riemann sphere at that point. So that expands it even more. And then, yeah, just what to say about that. I mean, just trying to think. I mean, obviously, when we're dealing with the Riemann Zeta function, that's just connected to the scaling factor. So we think, well, maybe we have to multiply it by the initial values or the subsequent values for the megaparsecs expansion rate of the universe. But actually, I don't think we need to do that. We could just keep, because the defined structure of the Riemann Zeta function means that there's points at every point in space. You know, no matter how small you go, that you're always going to get an answer. So I don't think there's any need to really scale the zeta function. It just is the background in which the sphere scales. So yeah, there could be a huge amount of work there. Then we can reproject the zeta function back onto the tangent space, and now we have a complex manifold superimposed on the universe. That could be very interesting in terms of, you know, like I said earlier, lining up those staves maybe with the periodic redshift to see if is there a connection? Is the periodic redshift somehow based on the zeta function? And I mean, it's possibly not based on it at all, but it could be interesting. then we could also create some graphs of like the interior of the sphere and see which kind of lines and loops come out of that, and see if they also map to the periodic quantized or the quantized redshifts. So I think there's a lot of work to be done there, and so I'm excited. So do you have any questions about the results?
Yeah, yeah. I think there are few clarification. I'm thinking about two. They may be late, maybe more, but after probably next week or the following week, we'll again go through that. But one of them is that one interesting thing I found was that the surface area, the volume have pi square factor. Normally it has only pi. So the hypersphere, you have pi square. So is there a specific reason why it comes like that?
Yeah, well, I guess if you look at, you can just, these equations for hyperspheric geometry, for volume and such like, have been already, how do you say, derived, like by
physical. Is there a physical significance for that when it comes like pi square versus pi, geometrically or physically?
Well, if you think of
so does it mean that it's more than 3D? I mean, like pi means it's a Euclidean geometry.
Yes.
4/3 pi r cubed is your volume. Whereas in this case, this pi square comes there. Also, the 4/3 factor is changed.
Yeah, of course. I mean, well, you can kind of look into that, how it's derived. I'm not sure. All I know is they derive the surface area of the hypersphere as the differential of that equation that you're talking about. And I've kind of I'm not sure if I looked into how that is specifically derived. I may have done, but if I have, I've completely forgotten. So, but I think you can just look up volume of hypersphere. I think there's an entire Wikipedia page dedicated to that specific subject, and it gives you for like 3 dimensions, or well, I guess it wouldn't do 3 dimensions, but 4, 5, 6, 7. I think it goes all the way. It goes up to quite a high number. But yeah, exactly. So what we're talking about is a volume. Like obviously, if you're talking about the volume of the sphere, which you correctly said there is one thing, but then when we move up to another higher dimension, you're going to have, factors of squares and such like. And I was doing some equations. And I'd have to probably run and get the notepad to check exactly what they were. I was looking at some equations for volume and can't remember, but I remember taking derivatives, and the whole thing might not be as complicated as it appears. It all sort of folds back into itself into like circumferences and those kind of ratios. So, but still, no, it is tricky to get your head around. I mean, I can go look for that. If you want to take a break,
yeah.
go look for that.
Yeah. One more thing, and then we can take a break. I mean, probably we can think about. You mentioned that a volume gives a better thing than the surface area.
Yes. Yeah.
For especially pressure entropy. I mean, you would think that because
just to make
the surface area is more the surface tension, whereas the bulk will be more volumetric. So
I agree. Yeah, this is it. So that's something that's a bit confusing, right? So when I'm saying that the volume is better in terms of, it seems to be better in terms of the unification. It's in terms of the unification of the gravity and electromagnetism. rather than pressure and volume, you know, because we can take the pressure and volume of the surface or of the whole hypersphere, because you know, the surface area has volume from our perspective. It is actually the normal XYZ coordinates of space, so that is volume. But then the hypersphere is an extra dimension of volume, obviously. So it is a bit strange that it's the volume equation that seems to show better, how do you say, conformity with, if you like, with the coupling constants of the gravity and the Coulomb force. So yeah, I do find that a bit strange. I mean, you know, it's interesting because we're talking about surface tension being gravity. There was actually an interesting paper I saw on ResearchGate written by a woman, and I'd have to go and look it up. I haven't been able to find it again since, but basically she was considering, and there's been not a huge amount of research done into surface tension gravity, but there are a few papers out there that look into the subject. And her one was kind of interesting, I thought, because she was looking at, like, imagine that our universe is just the surface of a lake, if you like, that is four-dimensional. And then, so I think she was thinking like the pressure then, you know, because there's a cohesion on the surface of the lake, which is the surface tension. And so it's an interesting concept that our universe is, the space in our universe has this tension. And so I'm kind of expanding on that work, but obviously it looks from, I can't really say for sure, but I think that the universe or the sphere is a bubble, not an actual droplet, but it would still have some sort of an internal pressure anyway, which seems to be alluded to from the discrete Legendre transforms that I showed on screen earlier. So it does have some sort of internal pressure. And so it seems like the pressure on the sphere is related to electromagnetism. And let me think. And then the force being generated, which comes from the surface tension divided by the area, in a sense, gives you this kind of global gravitational force. And then, but yeah, it gets kind of a little bit complicated. But so there is this pressure the pressure. Let me just think. Yeah, no, I was thinking about something there, but I've kind of forgotten what it was. But it was about pressure and the force of the electromagnetic. No, it's gone. It might come back to me later, though. So yeah, I think we'll take a quick break and then we can come back.
About 10-15 minutes. Yeah. Okay.
Okay. Cool.
Thank you.
I'll just stop this. Okay. I'm back. Where are we? Oh, yes. So, yeah, I remembered what I was going to say. So, on when we take the volume, that is, you know, megaparsecs to the fourth power. And so even if we, let's say it's, or sorry, well, even gigaparsecs. So let's say it's 212 gigaparsecs to the fourth power. That's obviously, then we need to multiply, or, you know, take the fourth power of that number, which is much bigger. And that increases the pressure as well. But the relationship between the gravitational constant and the Coulomb force, between the two coupling constants, that only becomes apparent when we're looking at one of those dimensions, if you like. So it's essentially talking about because if we take the fourth power, the number is too large. The ratio is only properly matched up when we're looking at maybe, you know, one of the dimensions. So I think that's interesting. It'd be even cool if we could get down to 0 dimensions, because then we might be able to find the exact Coulomb force for, you know, like a particle without it being related to another particle, although maybe that doesn't mean anything. But it's also not really clear how we could do that. I know I was talking about where you take the square root and then the cubed root was what I was looking for. But so you can either take the, that's why we're taking, like, let's say the cubed root of the surface area, because we only want one vector, one dimension. So, I mean, and that's interesting because, well, I suppose.
Cube root of surface area or the volume?
Well, yeah, but well, there's two. So we could either do the well, how do you say, like the fourth order root or the fourth root of the volume, or you can do the cubed root of the volume, and that seems to give a relationship that's quite close to the Coulomb force between a proton and an electron, and then yeah, like the fourth root gives just between two electrons. So then we could ask, does the fifth root give the actual force of the electron just by itself? But really, that doesn't make a lot of sense, I think, mathematically, because when you get, you know, you'd have to think about it. But yeah, maybe I'm going to give it a go, but it's not entirely certain.
One of the things, yeah, I'm thinking this paper I was talking about the exact solution of the Schrodinger equation, again, the live thing, briefly mentioned. Right now, I got the excellent review. So it will appear 1 to 2 weeks. That talks about how in the flat space, when the potential energy is 0, both the fixed equation as well as the Schrodinger equation match differently. And then you can define.
What's the first equation? The fixed equation?
The FIC, the diffusion equation. You know, the FIC diffusion equation also consider about a concentration, the space variable of the concentration, space derivative of the concentration equal to a time derivative of the concentration, you know, to certain order. So we have the famous Fick's law of diffusion.
Yes.
The second law, called the second law, the famous equation that all the diffusion people use. Where you have
but
diffusion.
Isn't that the point of the Schrodinger equation?
Yeah. So the error function.
Wait.
Yeah,
I'm asking a question. I want to know, isn't that the whole point of the Schrodinger equation, that it is based on the diffusion equation?
Probably, but it is not obvious, and people are not why the departure occurred, and you know why that disconnect, and after that people didn't talk about it. That's what I want to bring it back and see why it happened. One of the reasons is that this is true only, you know, this I don't know how Schrodinger solved it or whether he knew about a fixed equation, but I don't see, in some places you may have seen, but I have not seen in the real literature of the quantum mechanics. Nobody, the quantum physicist talks about the connection between the two. As far as I know, the few quantum courses, the fundamental quantum mechanics that people talk about, quantum physics, right? The professors they never mentioned about this aspect. So I
Well,
think it's
I'd
a
just
very
like to
important.
ask you a question there before you go on. You know, like I don't know that much about this subject, so I'm really just asking like kind of clarification questions here. But it seems to me, that what I'm trying to understand is the Schrodinger equation is based on the diffusion equation. Okay, and this is a well-known fact. So is that diffusion equation that he's using different to this other Fick equation you're talking about? Or like, is there a reason why you want to connect it to that equation? Like, are you saying, oh, he should have used this equation? Or are you saying what? I'm not sure.
Yeah. Not the, see, not at least the interpretation way. Actually, the reviewer would know. I think he seemed to know about it, but he never mentioned in that this particular equation was solved before, in the literature.
So
He would
it's a
have brought about.
particular equation. You're acknowledging the fact that Schrodinger used the diffusion equation.
Might have. Yeah, I would take it. I would, because
equation that why didn't he use this one? So your contribution is applying this different, maybe better equation, maybe more accurate, to the Schrodinger equation, and what does that achieve? Like, what are your objectives in doing that, or what were the results? Like, what have you found?
Yeah, good question. So now we can redefine, at least in the flat space, what that psi value is, because we really don't know what that psi value is.
Oh, when you have that psi symbol, psi for the wave function,
that's just
like, it's just like, that's the wave function. We just put that in there.
But
that's the wave function. Who knows?
But we can, but in this case, we can get a physical understanding, little bit more physical understanding of the wave function.
Yeah.
So that's a good, because it's like a diffusivity with a concentration, right? It's like a concentration, and you can connect with the diffusivity. So only thing is that you can have a very fast diffusion coefficient, could be very fast.
Right.
So it means that it defines some kind of a diffusion that's occurring, the wave function. So, I mean, we have to expand on it, but flat space, it means that you can say how the things pop out, the particles pop out. I mean, we have a hot PDP mechanism, which is more important, but it points to the fact that the wave means that the field, the psi is equivalent to the concentration for the field. So the mass has a field, right? The mass obviously has if there's more hydrogen here, less hydrogen here, it's going to diffuse, right? It's going to move to each other so that the concentration gradient is equalized. Different parts. Now the same thing.
Isn't the Schrodinger equation? I mean, obviously you can generalize it to a higher number of particles, but just on just dealing with one particle.
Yeah.
So
electron.
Yeah, the one electron. So that's diffusing over time, because in terms of probability, we don't know where it's going to end up. So that's the reason why we'd use the diffusion equation there. The question I have then is, like, let's say in the Marangoni flow research that I think I talked about previously, you take a drop of surfactant, you drop that into a petri dish full of water, and it diffuses out. So, and well, like the petri dish will have, like, because of the meniscus, it has a slight curve. It's not completely flat. But Are you saying then that if you know the difference between the surface, whether it's completely flat or slightly curved, that alters the diffusion equation, and therefore you could say something about the wave function?
Excellent.
Can you elaborate a bit on how that's done? Is that a component within the equation that's not within the diffusion equation that appears in Schrodinger's work? Oh, interesting. Please elaborate.
Yeah. So one of the things is that, actually I wanted to bring up the Marangoni effect. I mean, anyway, we'll come up later with respect to your own thing. Because that's another question I had. I forgot, but glad that you mentioned about that. We'll talk about a little bit later, because that's another part I was quite, enamored or interested in quite.
Yeah.
So the important thing is that this will serve as a good basis in the sense that what I'm saying is that the psi is like the field equivalent of the particle aspect. So if you have two electrons, like you have a bunch of electrons here, bunch of small number of electrons. So you have a difference in concentration of electrons, right?
Right.
So now I can use that as a diffusion, but also I can convert to psi, which is a field function, right, of the field of the electrons. So instead of using the electron as a particle, I can use as a field, right? So I have a very high field I have here, very, very small field, very low field here, right? So it will diffuse from the high field to the low field, very similar to diffusion. So you can convert the field equivalence of the mass diffusion, So
but
that is...
Sorry, these are really basic questions. But so electric charge flows from high potential to a lower potential. So okay, so are you saying if you have less electrons over here, that means that's a lower potential? Always.
Normally. Now there are like
reverse but isn't it to do with charge? Like you have lower, like negative charge here, positive charge here.
Yeah.
So there's always like, if you were to remove all the positive charges, you're left with negative charges. Do you know what I mean?
Yes. Yeah.
So in that case, so there's no real idea about like removing the electric field. It's always there. It's just either positive or negative. So then the flow flows that way.
Yeah, flow.
But you could say, so if you're saying like you have a potential energy which is mostly negative charges and a few positive charges, the higher charge will flow to the slightly lower charge. Is that what you're saying? Yeah, of course. Okay, continue on.
Yeah, this assumes, of course, the media is the same. It's a homogeneous media. Suppose the media is different here versus that's different.
Yes,
it depends on the media then. Yeah, it's in that same media. Okay.
Yeah, of course.
Which has all the other properties. Everything else is constant except that constellation. It's
like
very important.
Circuit or something like that. Okay.
Yeah, we have to always watch out for that because we have to ensure that that's the case, because that's not always the case, right?
Right, that's interesting.
Yeah. So the other aspect, the important aspect is that what happens if we deviate from the vacuum? So the vacuum, we say potential energy is 0, but what if the potential energy is not equal to 0? So what happens then? So what happens then is that we cannot solve that particular fixed equation. It will not have error function value, but it will have what the Schrodinger has given. And that means we have to have separation of variables. If you go to quantum mechanics fundamentals, and I listen to the thing, the only way we can really solve Schrodinger equation to some degree is to have separation variable, which means that the time is different from the space. So we solve for the time psi of t, and then we solve for psi of xyz or psi of r. We have to solve. We have to separate that, and it's a fundamental thing. Diffusion equation, differential equation. You can do separation of variable. If it is f of f is a function of f of x comma t, you can separate into f of g of x times some other function psi of x. So you can separate the variable and solve that problem. That's the way it has been solved. And the good thing is, in that case, not equal to 0, your flat space, the tangent space, and I'm changing a little bit so that we get to the point. But there are some in between things that we can figure out. But your tangent space and your hypersphere comes into picture, because now the hypersphere is, your tangent space, it says vacuum. That's a zero potential energy. Now, if we add potential energy, you can interpret that it curves the space, it curves the flat space.
Right.
So then v equal not equal to 0 can become like your hypersphere. So that curvature. Now I have solved that. We'll come to it later. But the time and the space, like I said, the time is a vector tensor, probably rank 6 tensor or so. But you can come up with like a symmetry group where you have 8 by 8, and in that one you have time and also the space aspect. And the space aspect has charge and the mass, charge and the density. The charge density,
of course,
and also the mass density. Okay,
right.
So it has in there, and what happens? We can look at that, and you can see what v not equal to 0, that you have the vacuum density changes. Whenever the vacuum density changes, the flat space starts curving. And that curving is according to relativity. So Einstein didn't describe like that, but I think the Einstein thing comes there. That makes sense. Why it deviates from Newton is that when it curves, it becomes gravitational, because now you have volumetric aspect that you're talking about. That's more gravitational. Whereas the flat space is more like surface area, which is more fermionic, or what you call the electromagnetic aspect, right? You can separate the electromagnetic from the gravitational thing.
Yes.
So I'm saying that your thing, the mathematics I'm developing, I think it will eventually match with what the geometry you are developing, the algebra I'm developing will match with the geometry.
That's great. So which I'm looking up Fick's equation here, and it's a couple of different ones. There's J equals to minus D, the derivative of psi divided by dx. But then there's
that's not the one.
Diffusion flux. So there's variations on the first law. There's the second derivation of first law for gases, second law.
Second law, I think.
Is the second law, is it?
I think so, yeah.
Okay. Oh, yes. The derivative of psi divided by the derivative of the time, which is d, and d is the diffusion flux, I think.
Coefficient, yeah.
Coefficient, yes, you're right. And diffusion coefficient, and then so we have the second partial derivative of psi divided by the second partial derivative of x. That looks interesting. And so this particular equation has not been applied to
the Schrödinger
equation.
Not that specific way I am doing.
Oh,
he may have considered that. He may have just, what happened was Schrödinger might have looked at it, and then you looked at, Minkowski was his teacher, right? So the Minkowski developed the 4-dimensional. So he looked at the Fick's equation, immediately struck his idea that should be Minkowski space, because the space and time are coming in. So he immediately jumped. No, it was not Schrödinger. It's Einstein's teacher. I don't know how Minkowski was related. Minkowski was related to Einstein, not Schrödinger. But Schrödinger might have known about Minkowski and also Einstein.
That's a big problem, though, with the Schrödinger equation, isn't it? Is that it's... Oh, well,
X, Y, C, T.
Which one is? I'd actually have to. You're better on the history of physics than I am, but you know the way. Is it difficult? Is the Schrödinger equation fundamentally quantum mechanical, or is it general relativity? I think it would be quantum mechanical, but then you have this issue where Schrödinger's equation is time dependent or something, or it's not. It should be time dependent, obviously.
Yeah.
Whereas general relativity and relativity aren't, you know.
Geometry. It's more geometry.
Yeah, in the sense that, you know, the general relativity is background independent. You can try, everything's relative. You can transform it any other way. But the Schrödinger equation is not background independent. It is time dependent. And that's an issue with a lot of these equations. You know, you have the Dirac equation and those kind of ones where you have to figure out how to incorporate general relativity with the quantum mechanics, and they do it, you know, quite well. And I think, well, certainly the Dirac equation is a good example of that. So that's been done for sorry, not general relativity, special relativity, and then so they still have to do it for general relativity. But yeah, so that seems interesting. But if the Schrödinger equation isn't time independent, then you can't, right? So it probably meshes well with special relativity, but not with general relativity. I guess that's what they're saying. But how does that affect your work? You seem to be talking about bringing general relativity into it through a curved sphere later. Yeah. So that's work you have to work out. So in terms of the flat space, obviously that's an infinite plane. With the hyperspheres, then the curved hyperspheres that are involved, have you what sizes are they going to be? Do the hyperspheres change depending on the size of the gases, or is it just kind of abstract? Do you need to know the radius of the hypersphere, or is that?
Yeah, actually, I want to bring in, and that is the very mind-bending thing.
Yeah.
Because I want to bring in, I have already a chapter in a book that's also going to come out in in a month or so. Right. Because they are delayed a little bit. That's a book in which I have hypothesized about the false vacuum and the true vacuum. So your flat space, this thing is a true vacuum. Yeah. Whereas this one is a, you know, so I want to bet that it's a false vacuum.
Wait a second. How do you envision the false vacuum? And because usually that's done with some sort of almost like a quadrature, like, you know, some sort of gradient. We're in a local minimum, and then you have another peak, and then there's the actual global minimum, right? And so the idea is, like, do we have enough energy to kind of, like, is the mass of the Higgs quark stable or metastable or unstable? And if it's unstable, then it'll just keep rolling down into this next dip. So does that suggest, I mean, when we talk about the local minimum, can that be a flat space? And then, like, how does that work? Are there just like different flat spaces, like, you know,
different potential energy?
What?
I'm thinking that it will be a different potential. This one is zero potential energy. Oh. The false vacuum will not have zero. It will be the potential energy will be not equal to zero.
But wait a second. Hang on a sec. Isn't the reason why the potential energy is zero in the flat space is because it is flat?
Yeah, but also you can think of this one. You can say, you know, that's what I'm thinking now. But I have to rethink about that, and doesn't make sense.
Rethink that, because that's a very good. That point you're making is very good. That is a very good point. So you want to be sure, if you're going to throw that out. Yeah. What if you're throwing it out? It's because you have something a lot better.
Yeah. I hardball these things. You know, I do hardballing and see whether that makes sense.
I know.
So I again review it.
I understand. I struggle with these kind of things a lot as well. You know, you have an idea, and then there's this other idea, And in order to get to this idea, you have to sacrifice something from here. And so sometimes it's just better not, you know, it depends on what you want. If the other thing is better, then move towards it. I'm just wondering whether the vacuum, false vacuum is like, especially if we've got the Marangoni flow catastrophe, I almost feel like the false vacuum is like surplus to requirements at that point, you know?
What's that?
What like, requirement? Surplus, like it's just another theory that's a bit, maybe it's like too many theories at that point. Like if the Marangoni flow catastrophe is real, then that's kind of good enough. You don't also need a false vacuum theory.
We have to see that. The idea of false vacuum is solved. Suppose this is a true vacuum, right? V equal to 0. Now, we can think about layers of flat spaces.
Yes.
So you have the lowest flat space is your true vacuum. Now, the flat space, as we note, so V not equal, the potential not equal to 0, the flat space is elevated. And this is your false vacuum. So you can think about that way also, that you have the lowest potential energy, 0 potential energy, and then you add potential energy, the flat spaces keep rising. That's one way to think about.
So they're being flat, but they're just like, it's like
they start curving. Of course, they will start curving.
Oh, they will start curving.
Curving eventually, but we can think of them as layers of flat spaces, and then when you assemble them together, they start.
Because you say layers, you say they curve, but they're flat. So I'm just confused. Which one is it?
I'm saying that. Okay, let me see. Like a paper, right?
Yes.
Let me bring some papers. I think that will talk about. Suppose I have, let's say I have the lowest here. The true vacuum is this one paper here, right?
Yeah.
And then I have a false vacuum that is up here, right?
Yeah.
Initially. But what happens is when they start interacting, like a diffusion or something, this will start curving to fit into that thing. And that's what I have to find. There should be a very fantastic mathematical thing which will prove that, I think. Although it may not be very easy.
Yeah.
You can prove that we can prove that these two together, when you arrange that, when you put the equation of the constitutive equations or equations of motion, that you start diffusion here, it will start curving and it will start forming that and form your finally, it's like the hypersphere. So it will start curving, and that's where the gravity starts coming. The gravity is not here.
Yeah, I don't know about that though.
There's no gravity.
Because we already have gravity, and
no. The gravity is an after effect. It's not a fundamental thing. Fundamental thing is electromagnetic.
You have it now. Like, you're not saying that you see this. Yeah, that's interesting. So you're saying that there's the potential of the You're not saying that the false vacuum is the tangent space and that the hypersphere is.
No. I'm not saying that. That comes later. Your thing comes later. This is just a starting point.
Yeah. Well, it's interesting. I mean, definitely take it slowly this time when you're formulating the idea. Good basis though, and just build on it like slowly, like.
Yeah,
kind of maybe look at how I'm approaching the work I did in this lecture. I don't know if that's any help to you at all, but maybe the next.
I think there's a lot to be done. To get to that point.
Just little steps. Extrapolations are really good, and then connecting one thing with the next, like you're doing. And if you can only make one connection, and it's solid. But you can't find it anymore. Just stop. Like one connection is good. Yeah. So But anyway, you've already written the papers. So
that will be fundamental. That will form the most fundamental basis you can fall back on all the time. And the reviewer seems to suggest that, although reviewer, give a very small thing, he didn't change anything, but he seemed to know because he's a good reviewer. Good reviewers are people who will not only point out what the problem is, but also give a way to go, right? So he did say, okay, you have to change title exactly to this. He gave a nice title. And also he said that your references are not, he didn't just say your references doesn't constitute. He actually put exactly all the references and how I should put numbers. He gave the whole list. So it was very nice. I think that's how reviewers should be. They just don't point out, but actual solution. I also try to do that for my review whenever I review, and I have bunch of reviews coming in now from the various journals, Journal of Physics, and they're sending out. But it seems to be quite interesting, like phonon thing. I think I accepted that. I got to review that. I have to review in a week or two.
Okay.
The other one, I think they accepted. I think it should be coming in. They're all interesting solutions.
Okay.
So I think, yeah, I think they know where I am. Where I am concentrating. I think,
Right.
the papers they are sending so far seems to fit in my interest. So we'll see.
Great.
So that's another thing. So by reviewing, I also understand. You learn more things, right? To check with your
Well,
thing,
that's it. Yeah, you see the
and
state of
that
the art
helps.
as well. Well, depending on which journal you're reviewing for, I suppose. But then, yeah, you see how like the you see, if you notice the way the direction, well, one of the directions the work on the anamorphic universe model is moving in at the moment is into these kind of volume, pressure areas, ideal gas laws, number of particles, temperature, entropy. So all of these things are very thermodynamical, right? And that's kind of your area of expertise as well. So would be interesting. Do you have any ideas on how to maybe expand on that?
So one of the things I say is that connect the legender. I was trying to do that. I was actually working on the legender to how to connect the legender transform with the Boltzmann. So I had written a little bit. I think I had to think a little more. But according to that,
But even
we can
it
use.
doesn't have to be like unique research that you're coming up with, but even just like standard stuff that you would apply in a different context, applying it in this context. Wait, don't interrupt me. Just let me finish my point. So something, yeah. So maybe you already know what I'm going to say. Yeah. So like stuff that like we normally apply in thermodynamics, but never going to apply it over here. That's entirely new. I'm not looking for like a new thing that may or not be accurate. I'm looking for stuff that that's like useful or potential or used a lot in maybe thermodynamics that deals with properties such as entropy and so forth, and then apply it to the pressures and volumes and entropies and temperatures that we already have, because we already have the data now. So for instance, I'm looking into maybe how do you say, like evaluate or come up with, calculate the grand potential of the hypersphere. So that's work I can do because I have the entropy, I have the temperature, volume, pressure, and so forth. The only thing I'm missing, I think, is the chemical potential or something like that, which I don't really know, but I mean, I could come up with another answer for that, or I could subsume the chemical thing into the grand potential and say, well, this is the value I've got. This value equals the chemical potential times the grand potential, or something like that. So that's kind of what I mean. If you have any ideas, I'm not asking for them now. I'm just mean in future, like if you given your kind of expertise in this area, I'd imagine that quite a few different kinds of equations and applications that might be useful. Then again, maybe not. I mean, we'll just see over the next.
See, one of the things in entropy is connected with temperature, right?
Yes.
Like ds, s equal to del del q over t.
Right.
What the del q? I'm saying that you can convert to a kinetic energy,
Okay.
and then you can express that in terms of legend. But there are some people who have done that before. But the
Okay.
main equation, I think, is the Maxwell forms of equations. I don't know, the Maxwell equations of thermodynamics. I don't know whether you have come across that, which just
Yes.
says the
Sure,
partials.
sure.
Yeah,
Yeah.
yeah. So the partials of, for example, the volume and the temperature, they are connected, with the
Oh.
entropy, and there are like four of very similar to the Maxwell equation of electromagnetism. It's a Maxwell
Oh.
equation of thermodynamics, which connects
Oh.
all that. I think that will be quite useful.
Yes.
But he didn't connect somehow that temperature to the electromagnetic frequency. I think that's something that's lacking.
Oh.
Although they use a very simple thing, like people use KT, which is the Boltzmann uh, Boltzmann law, to the Planck law equal to h nu, KT equal to h nu. But I don't think it's that simple. There's some there's
But what
something
about the
missing in
fact
there.
that if you have like, I don't know, electric
People use
current
that.
or something, you can convert that into hertz, and then you can convert it into joules, and then joules into Kelvin. So
Yeah,
you already have like a direct relationship between electromagnetism and temperature there.
temperature, radiation. For radiation,
Oh
and
yeah.
you have Stefan Boltzmann equation, which sees that T to the power 4 law, right? Stefan Boltzmann law, T to the
Yeah.
power 4, power is the power that's generated. I
Oh.
think you have to do that, I think. What I'm saying is that you have to use the power law, T to the power law, and convert the power into energy, and then equate that to h nu. I think that will be much more, because we are talking about radiation. So we have to talk about the radiation law, which is T to the power 4. I don't know why people are not, I don't know, I have not seen that. Maybe somebody did that, but I have not seen the general literature, the
Oh, but you
normal
can do it.
things. I have
Sounds
not
good.
seen that. Yeah, you
That sounds
cannot
good.
equate
Yeah.
KT equal to h nu, but instead you should use Stefan Boltzmann
Wait a
power
second.
law and then equate to
Oh,
radiation,
the error
equate
law,
to
is that like
Planck
an
law.
is that not an asymptotic curve or something? Or sort of, am I saying that right? Not asymptotic. Is it the asymptotic curve?
Yeah,
And the parallels are usually
T
like
to the
that.
power 4. T to the power law. So if the sun, the radiation from sun is coming to Earth, right? It
Yeah.
follows a T to the power 4 law. It's
Really?
sigma T to the power 4 law. It's called sigma. That's the power.
Well,
Power
you're
equal
saying that
to
the temperature to the power of 4 is the power? No,
is the power.
which is the
Is the
work
power
out there.
given by a radiating power given by a radiating object.
Oh,
Could
okay.
be.
That sounds
So
interesting.
that makes more.
You
Yeah,
should write that down, Rajan, as look into that, because you've got good
yeah,
ideas. You need to. That's good.
yeah. So I was thinking some time ago, but I departed because I got interested in these things.
Yeah, yeah.
But I think because these are very important, because there are so many areas like you are done, like a web, it goes all over the place.
Yeah,
But
yeah.
that Schrodinger I did right now, this paper will form one of the fundamental bases from which you can develop other things, slowly. So that's what I want to find out, what is the most fundamental thing that will then has a potential to connect with the rest of the things, like you know about ideal gas law and the deviation from the ideal gas law, right? So the ideal gas law was originally from all these people who Boyle's law and Charles' law, different things. People put them together and made
Yeah,
into
yeah,
the
yeah.
ideal gas law, right?
Yes.
Now, there is a deviation from the ideal gas law
Oh,
for non-ideal gases by
yeah.
using virial equation. So it connects it corrects for the volume. There's a correction for the pressure. It has correction factor in there. They adds a plus A plus B like that. And then you have something called the Weyl equation. That Weyl equation gives more for non-ideal gases. So ideal gases had to follow a lot of, very critical, important things, right? I mean, it is not valid for a real system. Like if you have a gas just in a gas chamber, like a normal enclosed gas, small system, the ideal gas law is not fully followed there. The large system, yes.
It has to be open,
small system. You have to use a Weyl equation there.
So that's interesting, because what I'm using when I was applying what would we say about the hypersphere? It's enclosed, right?
Yeah, but that's large, right?
It's big.
Your hypersphere is big, so it should not be a problem. If it's very large, I think the wall effect. It's called the wall effect. You can say, because small systems, the wall is going to bounce back all the atoms back in, right? So it doesn't follow ideal gas law. It starts deviating from it. Because the wall effect is very large. But in your case, the wall effect may not be that high.
No, I don't think so.
Because it's very large. It's very large. It's going to affect the normal.
Oh, thank God for that. I don't have to redo the equation. That's all I'm worried about. Great. So that's the work you're talking about there with the diffusion fixed law and all that is different, obviously, to the other work you're doing with the what is it again, with the time vectors and
that's another thing. I already put that the OJPS already have put it online.
Great. Send me a link for that.
I don't know whether we have time, and another time we can show. But we may, I don't know whether we have enough time.
Yes, so...
You want me to put it now?
What you can do is... another week. What you can do is if you want to post the link to your paper in the chat. But only problem I can warn you is that I have to send to them, because all the equations, when they put it in the online, they are, they are changed, like you did that, right? They actually put in wrong places, because there's subscript and superscript, so they don't match. So I'm going to write to them and then send them my document. Okay, well,
I don't know whether they have it. I had to check.
Yeah, in that case, hold off putting it in the chat, because that would be public for everyone to look at. But I mean, you might not mind that, but it'd probably be better if you go through the paper yourself next week and you can make your own corrections then if they're still needed, and then we can kind of go from there. But okay, I'm going to end the live stream anyway, because I think we've done 2 minutes.
Yeah, it's almost